Good morning, good afternoon, or good evening. I'm Cam, and welcome back to Quick IB Chem with Cam, your review videos for IB Chemistry, SL, and HL. Today, we're going to be talking about S3, which I dubbed the small unit, because this unit is only composed of two subunits, the periodic table and organic compounds. Woo! But unfortunately, as we'll see, this is a little bit misleading. Now, the first topic that we're going to review is going to be periodicity. Periodicity is basically just the identification of trends in the periodic table. So, for example, a trend would be ionization energy because it increases across a period and it decreases down a group. With these exceptions, if you don't remember ionization energy, go watch my S1 video. Electronegativity is going to increase across and decrease down, where fluorine is the MVP of electronegativity because it's going to be the most electronegative element in the periodic table. And if you don't remember electronegativity, you can go watch my S2 video. Now, electron affinity is going to be new, and electron affinity is the energy to gain 1 mole of electrons in 1 mole of gaseous atoms. Electron affinity increases across and decreases down, with the same exceptions as ionization. Now, the first electron affinity is always negative, meaning that it's going to become more stable after it gains that electron. The atom will, but the second one is always positive due to the newfound repulsion between the electrons. This is also going to be measured in kilojoules per mole, I believe. It will be in your data booklet for electron affinity values. Atomic radius is the size of the atom measured from the center of the nucleus to the outermost electron when the atom is bonded to itself. For example, if you had diatomic chlorine, which is a chlorine to chlorine bond. Atomic radius is going to increase down a group and decrease across a period. Ionic radius is the size of the ion, and you need to know that cations are going to be smaller than the parent atom because they have less electrons and a lower energy level. And anions are going to be larger than the parent atom because they have more electrons with the same energy level. Now, ionic radius, and you can tell what ion is going to be formed by any element based on its valence electrons. Now, ionic radius always increases down, and it has a staggered decrease across the group. Now, I call it staggered because, elements that have valence electrons from 1 to 3 are going to form cations, and elements with valence electrons of 5 to 8 or 5 to 7 are going to form anions, and 4 can form either one. But cations are going to be smaller than the parent atom, and anions are going to be larger than the parent atom. So when you jump from the cation to the anion, the size is going to go up, but it's still going to be an overall decrease across because you're gaining more protons that pull tighter on those the electrons. Now, melting points for group 1 or your alkali metals, it's going to decrease down, and for group 17, your halogens, it's going to increase down. Now, this is because metallic bonding gets weaker and covalent gets stronger because of higher molecular mass. And you can see I boxed these in because these are kind of general 5 that you need to know, along with this added one. And these are all going to have the exact same increase across, decrease down, but the atomic radii and ionic radii are going to be different, and they increase down and decrease across. Now, the next thing we're going to talk about are nuclear charges and oxidation states. So nuclear charge is the same as the number of protons in an atom. Effective nuclear charge is what electrons actually feel in terms of electrostatic attraction. To find your effective nuclear charge, simply subtract nuclear charge by how many electrons were in the previous energy levels. So, let's say that we have an atom with 12 protons. Now, this first energy level, 1s, is going to have 2 electrons, and so it's because it's closest, it's going to feel the full nuclear charge of plus 12. But because of the electrostatic attraction between them, it's actually going to shield some of these electrons from that nuclear charge. And so all you're going to do is you're going to take the amount of protons and you're going to subtract them by the amount of electrons. So 12 minus 2 is going to be 10. And the same thing happens here. 10 minus 8 is going to be 2. Now, oxidation states, which I say oxidation state the number, is the number of electrons an atom or ion can transfers, or have transferred in a bond. Now, in ionic compounds, this is equal to the charge of each ion. For example, NaCl, Na has a 1 plus charge and is going to have an oxidation state of +1. Yes, it's specifically +1, not 1 plus. They swap it for whatever reason from charge to oxidation state. It's really dumb. Now, Cl with a, oh, excuse me, it's not supposed to be a 1 minus 1. This is supposed to be a 1 minus charge, is going to equal a -1 oxidation state. Now, in covalent compounds, you assume it's actually ionic. Remember that this is an assumption, so it's not exactly accurate. The most electronegative element is going to get the negative charge, and then unless it's a polyatomic ion, all the oxidation states must add up to 0 when the compound's neutral. Elements vary compound. The specific oxidation state of elements can vary from compound to compound. Except, fluorine or goat, our MVP of electronegativity, is always going to be -1. O is typically going to be -2 unless it's in peroxide or H2O2, where it's going to have an oxidation state of -1. Hydrogen is going to be +1, and unless it's a metal hydride, where it's going to be a -1, because that Na, or the alkali metal, is going to have a even lower electronegativity. Now, elements bonded to themselves have oxidation numbers of 0, because neither of them are transferring. They're going to be the exact same. So oxidation numbers you might also see on the exams, and I remember the difference by oxidation numbers or oxidation Roman numerals express the value of the charge the same as the oxidation state, except they use Roman numerals instead. They always use this with metals that form multiple ion/ionic compounds, because metals can form different oxidation states. Now, as an example, copper oxide, or Cu2O, is going to be copper 1 oxide, because O is going to take a -2 charge, so there's going to have to be, if it has an oxidation state of 1, there's going to be 2, or if there's 2, then you have to know it has an oxidation state of 1. And for copper oxide, right, Cu and O, you have to know, that it's going to be a +2 charge, so you're going to have copper 2 oxide when you're naming it. Now, alkali metals are highly reactive and only increase in reactivity going down, because they have a lower ionization energy, only 1 valence electron, so it's going to be easier and easier to just pull that single one off. Alkali metals are soft, malleable metals that conduct electricity and heat well, and they react with H2O and to form hydrogen gas and an oxide. For example, we have solid lithium combining with water to make 2 lithium ions that are dissolved in water, plus 2 hydroxide ions dissolved in water, and hydrogen gas, where OH is the oxide. Now, the oxides of alkali metals are also going to be a similar process, where general for nonmetals, or this is a general trend for nonmetals, where you have the oxide Na2O plus water is going to make the NaOH, which is going to be a strong base, plus hydrogen gas. And this is still considered an oxide, sodium hydroxide. Now, your halogens are highly reactive but decrease in reactivity going down, because the higher molar mass equals stronger INFs. And so you're going to have stuff like going from gas to liquid to solid for diatomic fluorine, bromine, where bromine is going to be a liquid, and iodine is going to be solid at room temperature. As you see here. And they are strong oxidizing agents, and they can replace each other in bonds according to an activity series. Now, halides or halogen ions can be detected in solutions through silver nitrate solutions, where you have a silver nitrate solution where the nitrate is going to be a spectator ion, which is why it's not represented here. And it's going to, these two aqueous or dissolved ions are going to bond together to form AgX, where X can equal chlorine, bromine, or iodine. Now, if it's silver chloride, it's going to be white, or the solid, right, is going to be white. If it's silver bromide, it's going to be cream, and if it's silver iodide, it's going to be yellow. Now, how do you know if stuff is an acid or a base? So remember, across the periodic table, so metals form bases. Metalloids generally are amphoteric, which means they can be acid or base, and nonmetals form acids. So basic amphoteric acid. Basic oxides and acids react together to form a salt and water. We see lithium oxide plus 2 hydrogen fluoride to make 2 lithium fluoride and water. So all rainwater is naturally acidic, but acid rain specifically is when rainwater has a pH of less than or equal to 5.6. This is caused by sulfur from fossil fuels and nitrogen from combustion engines, combustion for sulfur and nitrogen oxides, which combine with water to make acid. So oxides are going to be anything with the oxygen in it. So this sulfur oxide is going to react with water to make H2SO3, which is an acid, and you're going to have a similar process for a combination of water with nitrogen oxide. Now, also, carbon dioxide causes ocean acidification, and this causes reproductive problems for fish. Just a little fact that you have to know. So, next group that we're going to talk about are metalloids. These are intermittent properties between metals and nonmetals. They form a staircase on the periodic table. So, if we have the periodic table here, if you have a periodic table here, we're going to turn this pen, and basically your metalloids are going to be these guys. Where you're going to have a staircase going down like this, except aluminum is not a metalloid. I wish I could explain why. It's just now your transition metals. Notice the white border, so this is going to be HL material. Transition metals are physically dense, hard, and metallic. You got to turn the pen on. They are often related in chemical properties because d orbital electrons shield. Remember we talked about effective nuclear charge. Where you have energy level S electrons, with the exceptions of chromium and copper. Now they are able to form multiple oxidation states, as was previously discussed. And they are efficient catalysts. For example, you have platinum and palladium, and catalytic converters, iron in the Haber process for ammonia, vanadium 5 oxide and V2O5 in the contact process, and nickel and hydrogenation reactions, or manganese oxide and hydrogen peroxide, the decomposition of hydrogen peroxide. Now, transition metals also have a property called magnetism. Ferromagnetism is permanent magnetism from unpaired electrons aligning in parallel. Paramagnetism is partial magnetism from n-paired electrons that spin to create small magnetic fields. And when all electrons are paired, the transition metal becomes diamagnetic, where it repulses each other instead of attraction. Magnetism, magnets, magnetic fields are going to attract each other. You get the gist. Now, transition metals are going to form complex ions with ligands. Is also something you need to know. So now we're going to talk about complex ions and colored compounds, or color. So ligands are species that donate electron pairs, act as Lewis bases, to a central metal ion to form a coordinate covalent bond. These are called complex ions. Ligands can also replace other ligands. So an example of a complex ion is going to be copper hydrogen 6, and it's going to be a 2+ ion. Now, complex ions can also just be complex compounds. We have a transition metal ion. It's going to be connected to these two ligands, and they're going to form a neutral compound. So a coordination number is the number of lone pairs bonded to a central ion. So if you're ever asked to describe what's the coordination number for, copper in this, you'd say, oh, it's 6. Now, the coordination number is directly related to with the shape of ligands, and for IB, we're going to mostly focus on octahedral shapes for complex ions, although I'm not exactly sure if you'll see these other ones, so just know them. And as we can see, there's 6 different ligands who are all donating a single pair of electrons, and that's how you're going to get your coordination number of 6. Now, ligands can actually donate more than one pair of electrons. So a monodendate ligand uses one bonding pair to form a single coordinate covalent bond, like water. A bidentate ligand uses 2, and a hexadentate uses 6. So this is the color wheel. This is going to be the absorption spectra or of visible light, right? And so it's going to go red, orange, yellow, green, blue, violet. And if you remember from S1 when we talked about the electromagnetic spectrum, you're going to have the wavelength of a photon, which is, the light that you see. And as that wavelength goes down, you're going to increase in energy. So remember that. Colors are complementary / opposites on the color wheel, which means that if you see something that appears yellow, it's going to actually be absorbing violet light. So the color of transition metals and the complex ions is due to the split of d orbitals on unpaired d electrons. Now, originally, all your d orbitals are going to be of equal energy, or called degenerate. But the formation of complex ions causes repulsion in these orbitals into a higher and lower energy state. Because when you put on that one pair, it's going to cause repulsion. Then when the complex ion absorbs light, excited electrons jump between energy states. The color is complementary to wavelength. Always remember that. Please remember that for complex ions. This is caused by the color is going to be caused by the nature of the transition metal. What are its chemical properties? How many protons does it have? How many electrons? The oxidation state of the transition metal, the geometry of the complex ion, and the concentration of the complex ion. Now, this is the splitting that I was talking about orbital earlier, where d orbitals split to produce 2 high energy orbitals and 3 low energy orbitals. So as you can see, these areas are these portions are where electrons are going to be found, right? And so you're going to have electrons found here, here, and these are all going to be pi bonds. But just know that the lower 3 orbitals exist between the different axes, and the higher orbitals exist on the axes. So you might also get something for the absorbance spectrum of a complex ion, where your highest peak is going to, the absorbance spectrum of a complex ion. Now for this complex ion, its highest peak is going to be at about 520 nanometers. And so if you look at the color wheel, this means that it absorbs green light because it's between 520 is between 491 and 575. So it's going to appear red. And you can see on the side, this is the absorbance of the different wavelengths. So whatever has the most absorbance is what's going to be the most reflected in the color of the complex ion. And you can see wavelength increasing from 400 nanometers to 700. Now, organic compounds. Organic compounds are compounds made from carbon. Carbon is special because it forms multiple bonds with itself and other elements. Carbon-carbon bonds, carbon-hydrogen bonds are strong. They can form chains and rings called catenation, and they cannot have an expanded octet, unlike period 3 and below, which would make elements more reactive. Now, homologous series are compounds with the same general formula, but they differ by a CH2. They have the same chemical properties, but different physical properties because of an increase or decrease in molar mass and the length of the chain. Organic compounds with only carbon-carbon bonds are considered saturated, and those with carbon double bonded to carbon bond or triple bonds are considered unsaturated. And this just means like all the areas where bonds can go are filled, so it can't bond to anything else. Functional groups are responsible for distinct physical and chemical properties, and these are separated into classes. Now I didn't know where else to put this, but I want you to know that the solubility of organic compounds decreases with chain length. So, as we can see, functional groups are going to be separated into class, and they also have the name of the functional group. So look, alkanes are just going to be molecules that have only single bonds, or that have only single bonds. Alkenes are going to be molecules with at least one double bond, and alkynes are going to be molecules with at least one triple bond. Alcohols are going to have an OH group, and ethers are going to be a carbon chain represented by R, bonded to oxygen, bonded to another carbon chain. And notice how the names of the functional groups are different from their class. And remember these suffixes, you are going to want to remember these later. For a lot of organic compound, this charts like these are really going to be your friend. So I recommend finding a chart that you like and being able to study it for the exam. Now, there's going to be more. You have an aldehyde, which is called a CHO group. It's a type of carbonyl. Sorry. Ketones, which are going to be a carbon chain bonded to a carbon, which is itself bonded to double bonded to an oxygen, bonded to another carbon chain. This is also going to be a carbonyl. Carboxylic acid is called a COO group. You're going to have a C double bonded to an O, bonded to an O, bonded to an H. Esters are going to be C double bonded to O, but then bonded to another carbon chain. These are also a type of carboxyl. So this is going to be carboxylic acid, and this is going to be a carboxyl ester. So amides are going to have a C double bonded to an O, but that C is also bonded to N bonded to H and 8, or bonded to two H's. And the C is going to be bonded to another carbon chain. And typically this can be what's considered a terminal group. So these are going to appear at where you only have the arrow, the line. I'm really tired. I apologize. But where you have the line that goes out this way, that generally shows that this is the end of what other organic compound you have. So amine is just going to be an NH2 group anywhere, and so an amide is going to be a C double bond to an O bonded to an N bonded to two H's. At the end of a molecule, it's an amido, and amines are just going to have an NH2, which is amino. Amido. And the halogenoalkanes are just going to be alkanes with a halogen on them. And so notice how all of these are suffixes, but these are prefixes. Remember that. Your halogenoalkanes are going to make prefixes, not suffixes. And lastly, an arene is going to be a benzene that has one hydrogen removed so it can bond to the rest of the chain. And this is called a phenyl group. So IUPAC naming. The best way I can recommend starting for IUPAC naming is searching up some online guides, because there's a lot of different types of naming that you might have to do. But generally, this is the steps that you want to take. Now, the IUPAC name is the official naming system of organic molecules. The longest chain of carbon gives the root of the name, where 1 equals meth, 2 equals eth, 3 equals prop, 4 equals bute, 5 equals pent, 6 equals hex, 7 equals hept, 8 equals oct. So this is all going to be carbon-carbon bonds. So you're going to have 8 carbons straight in a row, or 8 carbons all bonded to one another. And then for the second step, you want to insert the following root according to the following, or insert after the root according to the following. So if it has all single bonds, it's going to have an AN. If it has at least one double bond, it's going to have an EN. And if it has at least one triple bond, it's going to be a YN. Now, the third step is asking yourself, what's the functional group? Now, use suffixes from previous charts, unless it's a halogen or alkane. And if there are multiple functional groups, one will become the principal functional group. This is typically at the end of the molecule, which is a terminal group like we talked about. The rest will become side chains with prefixes instead of suffixes. Functional groups that do not have to appear at the end / side chains are indicated with numbers to signify which carbon they are. And if there are multiple identical side chains or functional groups, then you will state all the carbons they exist on, followed by di, tri, or tetra, or if there are 2 identical side chains or functional groups, 3 or 4 respectively. And lastly, take the name where the side chains have the lowest sum. If something can be represented like 1, 3, you don't want to take like 2, 4, or 2, 5, or whatever it be. And then esters and ethers. Esters are formed through the combination of an alcohol and a carboxylic acid among a sulfuric acid catalyst. As you can see the reaction. Oh, okay. Well, there we go. As you can see the reaction right here, where you have concentrated hydrogen sulfate or sulfuric acid that allows you to go from one to the other. So we can see here that the formation of esters also creates water, because the OH group from a carboxylic acid will be hydrogen bonded to the OH group of an ester, so much so that they actually separate into H2O. And then after that, because these now need new electrons, they're going to bond to each other. And that's how you're going to get your ester. Now, the alcohol gets the first part of the name, where you change the ending to YL. So here you have ethanol, so it's going to become ethyl. And the carboxylic acid gets the second part of the name, changing the ending to ethanoate. So if you have ethanoic acid, it's going to become ethanoate. Put them together, you have ethyl ethanoate. Now ethers are created through the connection of two alkane chains, or what are called alkyl groups, via an oxygen atom. So the longer chain keeps the alkane name, and the shorter chain goes first and takes oxy. So here we had a methane, right? And at some point it lost hydrogen and bonded to an oxygen, and that oxygen bonded to this propane, and so it's going to become methoxy, and you're just going to keep the propane. Now, structural formulas and isomers. Structural formulas clearly show exactly how a compound is bonded. All hydrogens must be drawn out. Please do not forget to draw out your hydrogens. Skeletal formulas show the placements of carbons in functional groups, and these do not show. I'm sorry. That's not supposed to be carbons. That's supposed to be hydrogens. Now, unlike Lewis structures, these formulas do not display lone pairs of electrons. So if you were to write a written structural or condensed formula, the structural formula of, I believe this is pentane, would be CH3, CH2, 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 CH3, where you can see that each of these is bonded to the next group. So like you can know that CH3, and it's going to be bonded to CH2, which is bonded to CH2, is bonded to CH2. And the condensed structural formula is going to be when you take the repeating groups or the homologous series and you just smush it together. So then you get CH3, CH2, 3, CH3. Now the full structural formula is going to be drawn out like this, where you're going to have the full 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. I apologize. I don't know why I used it's hexanol instead of pentanol anyways, or pentane anyways. I'm really tired, if you cannot tell, but we're still going to get through this because chemistry is extremely important. Now, you can see how all the hydrogens are drawn out with all of their respective bonds. And the skeletal formula is basically just going to be these kind of diagonals, or these zigzag lines, where each vertice is going to represent a carbon. So if we were to draw this, or if we were to draw hexanol as a skeletal formula, you can see 1, 2, 3, 4, 5, 6. And instead of this, in a vertice has like a kind of chemical or functional group on it, this isn't going to represent a carbon. This is just going to represent the bond. Now, structural isomers are isomers that have the same molecular formula but different connectivities. There are three that you must know. For SL, chain isomers are when a molecule can be either straight chained or branched. The more branches there are, the lower the melting point and the boiling point. If you want an example, you can look at pentane, not pentant, pentane, 2-methylbutane, and 2,2-dimethylpropane. Position isomers are when the functional group can go on multiple different carbons. For example, there is propane-1-ol and propane-2-ol, where the alcohol goes on the first carbon or the alcohol goes on the second carbon. And our functional group isomers, which have the same carbon structure but could contain different functional groups. For example, C2H6O. Here you can form a CHO group, or you can form an alcohol, and you wouldn't know until you drew out the full structural formula. Now we'll get into HO topics. Woohoo! We need to talk about stereoisomerism. So isomerism, or the classification of isomers can be divided into stereoisomerism and structural isomerism. Where stereoisomerism is where have the same structure but a different arrangement in 3D space. Now, even this can be split up into configurational isomerism and conformational isomerism. Configurational isomerism is more important for IB. So first, we're going to learn that conformational isomers are made with rotations around a sigma bond, and they rotate freely. Now, configurational isomers are isomers that must break and reform bonds in order to change isomers. So basically, they have to break in order to become the other one. So this results in cis-trans isomers and optical isomerism. So cis-trans isomers occur through the limited or restricted rotation of bonds, often due to pi bonds and the vertical overlap of p orbitals. Cis isomers are species where species are both on the same side of the double bond. Trans isomers are species on the opposite sides of the double bond, or later opposite sides of the molecule. Now, for example, we have cis-butene. You have a C double bonded to a C, and you have a methane group or a methyl group on the top side of both of these carbons. Now, there's also trans-butene, where you have the methyl group on opposite sides. Now, notice how for highlighting that these are cis and trans isomers, all we did was take butene and we said cis or trans. So just add the prefix at the very beginning of the name of the molecule. Now, cis isomers are going to have a higher boiling point and are polar more often. Now, if you think about it, if you have a more electronegative element or a more electronegative group like a methyl than a hydrogen, this is going to pull more electrons. And so if you had like a really electronegative group up here, then all of these, all electronegativities are going to be kind of focused up on the top of the molecule than the bottom. I hope that makes sense. Now, trans isomers are more often nonpolar, right? Because these dipoles are going to cancel out with a higher melting point because of the molecule being more condensed. Cis-trans isomers also occur in cycloalkanes because of the ring system. Now, I want you to look up at some point, if you want to know more, see 1,2-dichlorocyclopropane and 1,3-dichlorocyclobutane. Optical isomerism is also optical isomers are also called enantiomers, and these occur when a compound has a chiral carbon in the molecule. A chiral carbon is a carbon bonded to 4 distinct atoms or groups. The only physical property that is different is its optical activity. The only chemical property different is reactivity with other chirals. Now, these are bonded tetrahedrally, 4 bonds, which is about bond to 4 distinct atoms or groups, and they can bond in 2 different arrangements, making them mirror images. This means they are non-superimposable, so no matter how much you rotate the isomers, they will never be each other until you break bonds and reform. Now, solutions of these enantiomers rotate plane polarized light, which is the optical activity I was talking about earlier. Which plane polarized light just means it's light going in one dimension, so either vertically or horizontally. And these solutions rotate them in opposite directions. So if you have a solution of one isomer, it's going to rotate it clockwise, and then the mirror image is going to rotate it counterclockwise. But these are going to rotate it by the same amount. Now, disastereomers are enantiomers which have different configurations at one or more, but not all chiral carbon centers. And this means that they are not mirror images of one another. A racemic mixture is when enantiomers are present in equal amounts in a solution. Remember how we talked about solutions of enantiomers rotating plane polarized light. Now, a racemic mixture is when both enantiomers are present and they are in equal amounts. So because of this, if one rotates it 50 degrees to the left and the other rotates it 50 degrees to the right, well, because they're in equal amounts, they're going to cancel each other out and lead to no rotation. This optical activity can be measured with a polarimeter, which detects the optical activity by measuring angles in a pure sample of an enantiomer. And I tricked you. I actually have examples for trans and cis, the cis-trans isomers and the optical isomers. So hopefully you haven't looked them up yet. So this is HL, but kind of not. And the reason I say this is because yes, these isomers are HL, but this structure is a 3D arrangement. It's called a 3D arrangement, and so it's going to be a 3D structure that even SL kids have to know, where you have these normal bonds, which represent one dimension or one direction from the carbon. This big triangle, which is going to represent coming towards you, and these kind of alternating or ever-growing lines, which represent going like backwards. So as you can see, this is a cyclopropane, which means it's going to be a triangle. And so cis, it's going to be on the same side bonded to the triangle, and if it's trans, it's going to be on opposite sides of the triangle. Unfortunately, I do not have the butane one. Now, enantiomers of butane-2-all, we can see that here the H3C goes on this side, and the OH group goes on this side. but the mirror image is going to have the OH group go on this side and the CH3 group go on this side. And no matter how much you rotate them, these will not be the same thing. Because even if you rotate this 180 degrees, well, now instead of coming towards you, this hydrogen is actually going backwards. So now we're going to talk about different ways to identify or kind of analyze compounds in the lab. And the first one we're going to talk about is mass spectrometry. I hope you remember this because this is from S1. These are the molecular scissors. Now, mass spectrometry gives info about molecular mass and the structure of the compound. A mass spectrometer turns compounds into an ion, which is typically 1+, by ionizing them and make sure that's a gaseous compound by ionizing them with electrons, and then they are detected after a magnetic field attracts the positive ions that are left. So here we can see a mass spectrometry for ethanol, and I want you to notice that if you remember, the molar mass of carbon is 12, molar mass of oxygen 16, and molar mass of hydrogen 1. So if you add all these up, you're going to get 46. Typically, the largest mass to charge ratio on your mass spectrum is going to be the molar mass of the entire compound. And mass spectrometry can give us information about the structure of the compound because we know that molecular scissors can make one cut on the atom and remove one set of bonds, right? So let's say hypothetically we were to remove this bond right here. So we chop off that hydrogen, and now we're just left with this. Well, hydrogen has a molar mass of 1, and so we can see that we go from 46 to 45 because we've lost that hydrogen. Now, if we were to chop off, let's say here, well, this is going to be 12 plus 1 plus 1 plus 1, that's going to be 15. So we're going to lose 15 grams from the overall compound, the molar mass. And if we look, well, we have 46, we have 31. And so, now we know that there is a CH group there, or CH3 group there. And it's worth noting that when you get these mass spectrum, you're probably not going to be given the compound, or you might be given the molecular formula of the compound that's formed, but you won't be given like the full structural formula. And so you'll be asked to figure out what type of bonds exist. And if you keep going down the chart and you keep removing things, you can see, kind of how all this adds up. And then you actually get a chart for this in your data booklet, where we can see that, what's going to be section 22 of the data booklet. And so, as we previously discussed, if you lose a CH3 group, you're going to lose 15 grams. If you lose an OH group, you're going to lose 17, which gets you this 29 here, and so on and so forth. So if you're ever asked mass spectrometry, always refer back to section 22. Now, the next type of analyzing data we're going to talk about is infrared spectroscopy. Now, infrared spectroscopy is used to identify existing bonds, whereas with mass spectrometry, we talked about finding the structure of the compound. We're just going to figure out what bonds are actually existing. So, when absorbing infrared radiation, bonds stretch and bend, or they vibrate. Is another way to explain it. And these vibrations are characteristic to distinct bonds when absorbing specific frequencies of infrared radiation. Therefore, absorbance can be used to identify bonds in a molecule. Further, all compounds are going to have a fingerprint region from 1400 to 400 wave number that can be used to identify the compound. Now you'd be asking, what's wave number? Infrared spectroscopy deals with photons, because infrared radiation is on the electromagnetic spectrum, comes from photons. And if you remember, photons are equal to the speed of photons have a formula where the speed of light equals their frequency times their wavelength. There we measure frequency per second. So that's going to be, how many peaks you're going to have per second. Whereas here, you're going to ask how many peaks there are per centimeter of the photon. So always remember that in infrared spectroscopy, we measure frequency by wave number. And this just means per centimeter. So if we were to look at the infrared spectroscopy of hexanoic acid, well, none of this means anything to us yet. But if we look at section 20 of the data booklet, where we can see wave numbers on the x-axis and the transmittance is going to be on the y-axis, which just means how much of it gets through. We can see that where there are dips, that's how you're going to know where your areas, what type of bonds you have. So if we go to this from this 3000 to kind of around this 3000 area, and we go down to our data booklet, we're going to be able to see that these are going to be alkanes, alkenes, and arenes. But it could also be a carboxylic acid with hydrogen bonding. So we're going to keep that in mind, and we're going to see if there's anything else that can prove that there's a carboxylic acid in the infrared spectrum of whatever this molecule would be. It's worth noting you likely won't get what compound in infrared spectrum is for on the IB exam, but you'll be given, asked questions. You'll be given a molecular formula and say, okay, identify what types of bonds there are. And so now we can see that there's a peak from 1,500 to 2,000. There's a dip. So if we go from 1,500 to 2,000, we're going to see that it's kind of up in the upper limit. So this could be either carbon double bonded to oxygen, which would satisfy what we know about the compound hexanoic acid, possibly having a carboxylic acid. Excuse me. And then lastly, if we were to look at the fingerprint region, if you remember, this is going to be like your 1400 to 400 wave number area. It's going to be this region right here where you have all these different dips and peaks and stuff like that. Just, apologize if that's a little confusing, but just now you likely won't have hexanoic, like the name of the compound on there. But we can see that hexanoic acid, carboxylic acid with a C double bond to O bond to OH, had a carbon double bond to oxygen dip at the appropriate wave number, and it also had dips at the appropriate wave numbers for the OH in the bond. Now, it's worth noting that absorption of infrared radiation is the cause of the greenhouse gas effect. Diatomics like O2 and N2 cannot absorb IR or infrared radiation due to the inability to become polar. So, i.e., because the bonds stretch and bend, they're going to stretch and bend in different ways and often become polar. If it can't become polar, it's not going to absorb that infrared radiation. Global warming potential compares to the amount of infrared radiation energy absorbed by 1 ton of a gas to 1 ton of carbon dioxide over 100 years. And so this is, per gas. Now, the last thing that we need to review is going to be H1 NMR spectroscopy. And get ready, because this is going to be pretty rough. So, hydrogen nuclei possess spin, kind of like electrons, which can exist in two states of equal energy. They can go up or they can go down, represented by up or down. However, when a strong magnetic field is applied, these two states have a small difference in energy. Therefore, they can absorb radio waves, the small difference in energy, and this can provide insight into the chemical environment of hydrogen atoms in a molecule. So because they have spin and they have equal energy, they can be manipulated with a magnetic field because of this spin, which creates a small difference in energy, which means they can absorb radio waves and therefore provide information. A point of absorption on an H1 NMR spectrum is called a signal and shows one hydrogen environment. So as we said, it talks about chemical environments. So it's going to show one hydrogen environment, which is kind of like the conditions of hydrogen exist in. The position where the signal occurs is called the chemical shift, measured in parts per million or ppm. Because electrons have their own spin, neighboring molecules affect the chemical shift of the signal, allowing us to identify where a hydrogen environment is located, because the different connections to whatever carbon the hydrogens are bonded to are going to affect the chemical shift of that hydrogen. And you'll know this using data booklet section 21. Now, the area under each signal is proportional to how many hydrogen there are in an environment. This is also called the integrated trace, and it can give the ratio of the number of hydrogen atoms in an environment. And lastly, adjacent hydrogen atoms' spins can spin the same way or opposite way of other hydrogen atoms. And this is called spin-spin coupling. Now, this creates splitting patterns that show how many adjacent hydrogen atoms there are. if there are adjacent hydrogen atoms, then there will be N+1 splitting pattern. Because these spins can go with or against each other, they can go up, 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 down, or down, up. Splitting patterns can be modeled using Pascal's triangle, which if you know from math is basically going to be 1, and then the second layer is going to be 1, 1, and the third layer is going to be 1, 2, 1, and so on and so forth. So if there are zero adjacent hydrogen, then there's going to be a splitting pattern of 1, and you're just going to see one signal. If there's one hydrogen, on the adjacent atom, then there will be a 1+1 splitting pattern to make 2. And you'll see this reflected on the H1 NMR spectrum. The type of splitting pattern is always referred to as singlet, doublet, triplet, or quartet. Please do not mess this up. I mess this up all the time, but the type of splitting pattern is always referred to as a singlet, doublet, triplet, or quartet, not 1, 2, 3, or 4. So this is what an H1 NMR spectrum is going to look like, minus this text. And so if we look here, we can identify that there are 4 different hydrogen environments in a compound. As with the other ones, you're probably not going to get what the H1 NMR spectrum is of. But we can see that because there are 4 different signals, there's going to be 4 different hydrogen environments. Now, I want you to hydrogen bonded to the same atom don't interact. Hydrogen bonded to non-adjacent atoms don't interact for splitting patterns. So as we can see here, there's the different splitting patterns. You're gonna have 1, 2, 3 for the first signal, and this is gonna make sense because if we were to know that this was the structure of propanol, well, propanol is gonna have CH3, and so there's gonna be 2 neighboring hydrogen atoms, and that's gonna give you 2 plus 1, which is 3. So that's why there are 3 different peaks. And that's why the splitting pattern is 3. Now, if we go to the 4th electron or 4th hydrogen environment, you're going to see that there's no hydrogen on the neighboring atoms, right? The only neighboring atom is oxygen. So 0 plus 1 is 1, which is why when we look at this shift, it's going to have a 1 on it. Or why this signal has a splitting pattern of 1, or a singlet. Now, if we use the chemical shift, the ppm, we can see that if we look at the first electron domain, right? Or, I want to use this one. That's the best one. I'm sorry, I should have looked at this beforehand. But, I really this one, we can see that sorry, I'm freezing up. But the first, or the hydrogen domain, or hydrogen environment, you have CH3, 0.9 to 1. Well, that's kind of where we're at. And so that, helped you identify what type of bonds there are. And then, I believe there's alcohol somewhere on here. Yeah, so 1.0 to 6.0, this is going to be a large chemical shift area. So if we look at our 4th electron domain, this occurs between that 1-6 area. So basically for H1 NMR spectrum, just always look at the section 21 and be able to see, okay, well, this occurs between 0.9 and 1.0, so it's going to be CH3. There's a splitting pattern of 1, 2, 3, so it's going to be a triplet, and there's going to be 2 adjacent hydrogen atoms. And then typically on some other spectrums, you're going to be able to see the area under it, or you might be told the area under it. And if you didn't know what the structure looked like, that's how you'd be able to know how many hydrogen atoms there are in that electron environment. And congratulations, we are through with the structure segment of IB Chemistry. So thank you again for joining me in today's video. There's a lot of different info, but I hope you remembered some of it. And if you didn't, hopefully you do now. I know there are kind of some hiccups in there, but if you thought this video was helpful, consider liking, sharing, or subscribing, but only if you feel like it was helpful and you might want some more. Thank you for joining me on Quick IB Chem with Cam. I hope you have a great morning, great rest of your morning, great rest of your afternoon, or a great evening. Goodbye.